So this is my part 3 of my videos on surface integrals. On this time, we are now in the previous two videos, we actually talked about surface integrals where we integrate a scalar, that's a function, right, of and over a surface, right? Now here in this video, we are trying to see how do you define the surface integral of a vector field, right, over a surface, and we have a name for that. We actually call it the flux. So we start by thinking about F is a vector field and let S be an oriented surface, right? I mean, I will explain in another video what that really means, what you mean by an oriented surface. So then the flux of F, the vector field through the surface S, okay, is denoted by this notation. And it's actually defined as the surface integral of the dot product of the vector field with n. What is n? N is actually the unit normal vector to the surface. So if you think of a surface, right, and if you think about like at any point on the surface, you can hold a sheet of paper, say to the tangent to the surface. So then that's like a tangent plane, and then you can think about a normal to that tangent plane. And if you think of that as the vector, right, and that is n. So if you take f dot n, it's a scalar product, dot product. So then the final result is actually a scalar. Then by we can use the definition of the surface integral that we used earlier, right, to find the Riemann sum. I mean, you take a small piece of a surface area, which is like a parallelogram, and then you actually calculate this will be the heights, and this will be, and then you have the Riemann sums, and you make these DSS, right, go to become small as possible, or go to the number of DSS go to infinity and cover the whole surface, and you have the surface integral. So now, so this is, so what do you mean really by we call it the flux. So really I mean, you can find a lot of definitions of the flux, but in terms of, well, first of all, if you think, what is this F dot n? So if you think of F as a vector field and n is unit normal, it is really the component of the vector field that we have in the direction of the unit normal. And the flux is actually defined as the amount of fluid flowing through a surface. So it's a measure of the amount of fluid. So if I think of a fluid, right, and then if you look at the amount of fluid which goes through a surface, and that is the physical meaning of that. I'm not going to explain it too much here, but we will learn how to calculate this, right? So first of all, we need a good way of calculating this. So the first thing to do would be, suppose we parameterize the surface using two parameters u and v. So if u and v are the parameters of the surface, right? Then we know that this surface area space that we are concerned, right, is really a parallelogram space, right? Creating by what? Well, they are really the parallelogram is created by the partial derivatives of the position vector r of the surface along u, and then times the partial. So the partial derivative of r with respect to u and partial derivatives of r with respect to v, they kind of form like the spans which span the parallelogram. And you know that when you have the parallelogram spanned by two vectors, right, the area of the parallelogram is given by their cross product and the magnitude of that. So really this becomes that. Okay, so that is RV cross RV magnitude. What about this? Well, if we can think about F and then dot, let's try to get N. Now we know that again, this is RU is actually along the tangent uh, plane of the surface at that point, and RV is along the tangent plane of that surface. So if you look at the cross product, then that is actually a vector normal to the tangent plane at that point. in the surface. So if you divide that by its magnitude, then you actually get the unit normal. So the unit normal, so now we can really plug in these things because we can replace this by this times du dv, right? Okay, and then we can replace the unit normal by Ru cross Rv divided by its magnitude. And then you can see that the magnitude will cancel off, right? And then you get F dot Ru cross Rv du dv. So that's our formula. So if you want to find the flux across the surface, what you do is first you parameterize the surface using U and V, and you look at the partial with respect to U and partial with respect to V, and take their cross product, right? And then that's a vector. F is a vector. Then you take the dot product between those two, and that's what you actually integrate on the region formed by the parameterization, which is in the UV plane, right? And that's a double integral in the UV plane. So now let's try to use that. Okay, so first of all, we think about let's our surface be the surface created by this. This is, we know that's a cylinder which goes to infinity at both ends, but we are going to block the cylinder at 0 and 3. So we are going to cut out the cylinder at 0 and 3, and then we get a surface, right? And suppose the flux is this. Okay, so first of all, we need to, so the key thing here is to parameterize the surface. So how do you parameterize the cylinder? So because this is the base circle can be, because this is a circle of radius 2, it can be parameterized by 2 cosine u, 2 sine v. It's like u behaves like theta, but I'm going to call it u here, right? Okay. And then basically we have the c, right? Okay, which is really the v, and uh, because there's no restriction on uh, the way it goes up until, of course, it's restricted at 0 and 3, but if you take any point on the cylinder, right, then v stands by itself, and then these two are restricted by the circle, so it's 2 cosine u, 2 sine v. So now if you take the derivative with respect to u, you get negative 2 sine u, and sine u derivative is cosine u, and the derivative with respect to u, partial with respect to u is 0 or v. So that's this. And then if you take the partial with respect to v, then this is 0 because there's only u in it, this has only u on it, and you get 1 here. So now I need to find the cross product. So I will leave it to that. If you find the cross product of these two vectors, right, you will get 2 cosine u and 2 sine u and 0. And you can check it out for yourself whether that is true. And now I need to take the dot product of my vector field with the cross product. So what I do is I'm going to just take the vector field is 4x and minus 2y squared and z squared, right? And I'm going to take the dot of that with 2 cosine u and 2 sine u 0, which is cross product, right? And when I do that, I get actually 8x cosine u minus 4y squared sine u. But when I'm gonna plug in for x, which is 2 cosine u, and y is 2 sine u, and I plug that in, I get this, which is equal to 16 times cosine u minus sine cube u. So now this is what I'm going to come and plug it up here, because that is your f dot r u cross rv. So if I plug that into here, then I actually get a double integral in the region, right, which is spanned by this. So we have u and v, right? Okay, and so now it's a matter of if you take the this. So I have I can take the cosine 2u outside, and then I have dv, and if I do the inner integral, which is just 3, and the outer integral will be, the 3 comes out in 48, and then cosine u minus sine cube u. Well, you can integrate this using the double angle formula that we learned in calculus 2. And how do you integrate sine cube u? If you remember this trick when you how to integrate an odd power of the sine or a cosine, what you do it, you write it as sine u times sine squared u, and then you convert it the sine squared u as 1 minus cosine squared u, and then you put u equals cosine, like another different substitution, say w equals cosine u. This is something that we do in Calc 2, and I'll leave it to you to do that because this is not the time and place to go through that calculation. But if you do that, you will get 48 pi. Okay, and that's the answer. So basically, the flux of this vector field through this surface is actually given by that. Okay. All right. So very good. So let's now, like we did in my video on surface integrals, when you have a function, not a vector field, there's a special case that makes things a lot easy. So let's look at the special case when the surface is actually given as c equals a function. So basically, when the surface is a function of xy. So remember in the previous one, the surface is not a function because it violates the vertical line test because it's a cylinder, right? Okay, this is a cylinder, it's not a function, right? But sometimes you get a function. If you have a function, then things become a lot easier because we have an automatic parameterization of the surface as xy f of xy. We learned that when we did parameterized surfaces. So when you do that, the R has a specific form, right? And then what will happen is then the RU cross RV part and F dot RU cross RV part. Okay, this whole integral actually simplifies to this, which is a very simple double integral involving x and y. But what is P? P is the first component of the vector field, T is the second component, and R is the third component. And then you have the partial of C with respect to X, because remember C is now a function of X and Y, and partial of Z with respect to Y. And you plug that and you do a simple double integral with the X and Y, put the X limits and Y limits as how it moves, and you straight away without any problem, like in the previous problem, you don't really have to take dot products and then do the integrals, but really this is the flux, that's it. Okay, so now let's do an example. So let's look at this vector field, and this has a vector field, and the surface is, suppose, is this. So now the surface is a function because it's solved for z equals x plus y squared, right? And then x goes from 0 to 1, y goes from 0 to 1. So now we are going to plug it here. So what do we have? So partial with respect to x of this is what? 1. Partial with respect to y with 2y. So 1 and 2y. And then p would be the first component of this, x squared, and q will be the second component of this, xy, and third with r squared. And so now when we put that in, we actually calculate negative p. So negative p would be a negative x squared. Partial with respect to x is 1. So it's negative x squared here. So like that, you have negative q dz, partial with respect to y. So q will be xy. So that xy is there. And if you take the partial with respect to y, you get a 2. Right, okay. So and so you get and you continue doing that, and you will have to integrate this, right? And first we will integrate with respect to x, and then you get this, and then you need to put in the limits 0 and 1, and then you get 1/6, and then you take that 1/6 and do the outer integral, that's inner integral, outer integral 1/6 of dy going from 0 to 1, and then you get 1/6 as your final answer. So the flux here is 1/6. That's it for this video, and so that concludes my 3 videos on surface integrals. So it's a very important section because surface integrals can be calculated. So thing is, we are integrating over a surface. In Calc 1 we integrated over an interval, right? And now we are integrating over a surface, right? And then in the first 2 videos we talked about how we we are integrating a, something with x, y, and z over a surface, and now we scalar really, right? And now we will learn that we are going to and how we want to integrate a vector field over a surface, and when that particular integral is called a flux, and we learn how to find the flux using this formula, right? And in the special case when the surface that we're dealing with is actually a function where z's can be written in c as fx is y, right? Like for example, the one that we did, c is equal to x plus y squared. Then we have a really nice formula for the flux which you can use and get the answer. Thank you very much for watching.